this is what we call the Hubble law. If I am here, the nearby galaxies are moving away from me. Again, few nearby galaxies are moving towards us because they're actually deviations from deviations from the Hubble law. But as I move farther and farther in the universe, the galaxies are also moving farther and farther away from me. And this is the simple form, and still stands, namely the radial velocity, how quickly something is moving away from me, is proportional to the distance to that object times a constant, which we now call the Hubble constant. And what that really means is that the universe is expanding. Namely, if objects are moving away from me, that means if I go back in time, they used to be closer. So this is a truly profound discovery. Again, it took several years for people to accept it, but we've been measuring redshifts ever since, and the universe is expanding. You can point your telescope, even these days amateur astronomers with a little spectrograph, you can point the telescopes and pre-faint the galaxies out there, and all the galaxies are running away from us. Not because we're so special. It turns out the whole universe, any observer in the universe would see the same thing. So, this is a profound discovery. Not only the universe is huge, but also it's changing in size. The universe is evolving. That means if it's getting bigger, that used to be, it was smaller. And the Einstein equation of GR mean that if it's now getting bigger, I can go take the equations back. And there was a time when all the galaxies, all the objects in a way, they were on top of each other. The universe was very, very small and very, very dense. So Andromeda galaxy actually, as it happened, coming towards us now, but some other nearby galaxies moving away. If I go back to half of the age of the universe, it was moving away, was half a distance compared to now, and it was moving away slower. And so, just introduce, there's very little math in this talk, but if I drove 200 miles from Columbus to how do you pronounce it, Louisville? In 3 hours, my speed is roughly 66 miles per hour. I did 80 at some time, but anyway. And then, of course, this is my velocity, this is my distance. That means that, in fact, the Hubble constant has a unit of 1/time. It really tells us, if I measure the value of the Hubble constant, it tells me how old the universe is. How long were I driving? Namely, if I am that far away moving with that speed, that means I had to start some time ago. So by measuring the rate of expansion of the universe, by measuring the value of the Hubble constant, I can now invert this and measure the age of the universe. So not only I have the size, but because the universe is expanding, I can get the age. And as I say there, it's easier said than done. Namely, people spend countless hours on the telescopes, on all the telescopes, many telescopes in the world, ever since Hubble has made a measurement. And the value of the Hubble constant, we're still working on it, but it used to be off by a factor of 7. Now we are kind of quibbling about a few percent. So again, we made a huge progress on measuring the value of the Hubble constant. So one of the reasons the Hubble Space Telescope was built was that because we could put a 2.5 meter telescope above 100-inch telescope above the atmosphere, we could now find these Cepheid variables, not just in nearby galaxies, but we could find them in faraway galaxies. The farthest away that Hubble has found Cepheids at this point is roughly 100 million light years away. It has a very good image quality, and that means you can observe faint stars and you can resolve them from other stars. So one of the original goals, it turns out, of course, Hubble has done many different things as well, but one of the original goals behind the Hubble Space Telescope was to find Cepheid variables in not just nearby galaxies, but other galaxies. Here's a picture of what we call M81 Pinwheel Nebula in a galaxy in northern sky. That's roughly 10 million light years away. It turns out these days, actually, we can do that experiment from the ground too. So this is what we call Large Binocular Telescope in Arizona. Each of these mirrors is several times the diameter of Hubble. Each of them is 8.4 meters. So Hubble is only 2.5 meters. And there's 2 of them, and they always look at the same spot. The whole building is rotating. So they can actually get many more photons than Hubble. They don't have as good image quality, but also our ability to do things has improved over the last 20 years. Computers are getting better and faster, and people are getting, maybe not slightly, they're not getting smarter, but they're slightly smarter how to use them. And so we can now measure these Cepheids. Again, I told you, they become brighter and fainter, brighter and fainter. We can now use LBT, not just Hubble, but you can use ground-based telescopes, although the very large one, to kind of conduct the experiments that Hubble was able to do for nearby galaxies, for faraway galaxies. And when you do that and you put it all together, each of these dots is a measurement of the Hubble constant. This is a compilation by astronomer John Hakra, who has done it several years ago. We started with these values of Hubble constant of about 550, which implied the age of the universe was only 2 gigayears, which at the time people already knew the Earth was older than that. So they basically rejected this whole cosmology business as being ridiculous. You cannot have Earth, which is older than the universe. However, what happened, there are several reasons. So there are several reasons for that. As you can see, basically very few people measured Hubble constant. Mostly was Hubble. He called it K. He didn't call it H. And then there was a breakthrough in the 50s when people realized there are two populations of stars. There's, unfortunately, nature provides, but also is malicious. Namely, there are two kinds of Cepheids, and one of them is brighter than the other one. And people were confusing the two. So Shapley, for example, was using population 2 Cepheids, and Hubble was using population 1. Anyway, this is where it kind of gets complicated. But then, ever since 60s, there were two camps for a while. They were measuring either 50 or 100. They both agree it shouldn't be 75, and of course value these days is about 75. So if you do that and you do 1 over value of the Hubble constant, the age of the universe, we also use the observation of the cosmic microwave background from the WMAP satellite. We put it all together. The buzz value these days is 13.7 billion plus minus actually less than 1 billion. So we also know the size of the universe. We measure distances of galaxies, and we also know the age of the universe. Universe had a beginning. The universe we are in had the beginning, and that was 13.7 billion years ago. Plus minus, I think it's 0.6 billion. And it took us quite a while. Now, science also is something that we, just because we made a measurement, the best thing I could do in my career, if I could prove it all wrong, that would be great. If I could, this is all wrong, you're just stupid, and this was a waste of time. This is would be the best day of my life. Okay, I wouldn't put it that way, but. So, we want science to make sense. If the universe is old, then there should be objects in that universe that are very old. For example, we can measure the age of the sun by looking at precisely at properties of the sun. It turns out the sun is really not super stable, but sun has little pulsations, very tiny, nothing like the Cepheids. And if we actually really understand these pulsations, we can understand the composition of the center of the sun, and then by running computer models, we can deduce the age of the sun, which is about 4.5 billion years. But that's much, much younger than the universe. We want to find some objects which are almost as old as the universe. These objects are called globular clusters. Early in the universe, for whatever reason, these very dense clusters of stars have formed. One of them, very famous, is called M13. You can see it through even binoculars in the Hercules constellation. And if we look at these globular clusters, they have objects which have to be old. Namely, they're called white dwarfs. These are objects that remain after the star has evolved. And they're also very faint and very cold. And the only way this object could be that faint and that cold is if they are also very old. And this is one of line of evidence. We have many others, but this 13.6 is actually very solid estimate at this point, and we get it from multiple lines of evidence. And one of them is, so white dwarfs are actually these tiny objects here. That's why they put circles around them. There are very many bright stars in the globular clusters, but some of the more massive ones have evolved and left the white dwarf by now. Now, another neat thing about astronomy is that because the speed of light is finite, namely 300,000 kilometers per second, when I look at far away object, I also see it as it was a while ago. Even when you look at me now, you can see me maybe a nanosecond, you really see me in the past, namely a nanosecond ago. By the time you look at the sun, you see it as it was 8 minutes ago. By the time I look at a nearby star, I see it as it was several years ago. By the time I look at M101 galaxy, this is the one on the poster. This is again the beautiful picture from the Hubble Space Telescope. That is not the picture now, in the cosmic time, if you will, but that's how this galaxy was 21 million years ago. And if I push it farther and farther away, I can see, if I am able to see very faint object, very far away, I also get to see universe as it was young. I can actually see the evolving universe by observing objects which are very, very far away. So at this point, the record is, at some point we switch to redshift, but that doesn't matter. But in terms of units, we are at 13.7. We get to see objects in the universe as early on as about 600 million years after the Big Bang. And the whole idea is to push this farther and farther away. Because now we're understanding, I won't really have time to talk about it, that the universe really started as this hot and dense object where there were no galaxies, there were no stars. And of course, by now we see galaxies and we stars. We want to see the first epoch of star formation. We want to see the first stars being born and then dying and exploding as supernovae. These are so-called gamma ray bursts, which could be a separate talk, but I won't talk about them here. So here is in one slide the history of the universe. The universe really started at some point, for whatever reason. You know, we don't have physical description of what happened before the Big Bang. We can take our laws of physics and push them as early as 10 to minus 45 seconds after the Big Bang. But then the laws of physics are the one that we know break. But of course, the idea is that we'll be learning, you know, better and better. The universe actually underwent, again, this is kind of separate talk, a dramatic era of inflation, where the universe increased in size by a factor 10 to the 30th in very short time. We actually need this for several reasons. For example, I don't really want to go into that, but there are a number of observations that actually require inflation. Then after that, the universe still expanded, but at much more leisurely pace. This is kind of the pace that is expanding now. At the time was very hot, very dense. We see the leftover radiation from that called cosmic microwave background. Then there was a time what we call dark ages, namely there were no stars and there were no galaxies. So there is nothing to produce light, and therefore it's called dark ages.